One more video on related rates. A firework is launched at the rate of 12 feet per second from a point on the ground that is 25 feet from an observer. Find the rate of change of the angle of elevation when the firework is 20 feet above the ground. Okay, so let's see what we have here. Here's the situation. Firework let off at a certain point that is 25 feet away from a person. So y is going to be 25 in this case. And the question is asking to find the rate of change in the angle of elevation. So that's this guy. When the firework is 20 feet above the ground, so that would be x would equal 20. Okay, so let's organize this a little more. Oh, I didn't mention this. The rate at which the firework is being launched there is 12 feet per second. So that's the derivative of x. Y is 25, asking us for the derivative of the angle. And we want to know when that happens when x equals 20. Okay, so we need an equation that has the angle in it so we can take the derivative of the angle. Theta is just a variable, so, treat it like x, but there's already an x in this one, so treat it like another letter if you don't like theta. And we need to use these two as well because we have information about them. So we're going to have to use the tangent because that's opposite over adjacent. So when you take the derivative of this, it looks like the derivative of tangent is secant squared. And remember, when we're dealing with these with respect to time situations, we took the derivative of that angle with respect to time. And now this needs the quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's my shortcut way. So when we took the derivative of the top, these are just to the first power. X to the first power is just going to be 1 times x to the 0 power. We take the derivative of x. We're doing things with respect to time. So that's why we end up with the dx dt. And then the top minus the derivative of the bottom. The bottom is the same. It's just y to the first power. And then the bottom squared is y squared. So left side is just a straight derivative of tangent. Right side is quotient rule. Okay, we were given a lot of information here. Y is 25. The rate at which x was changing was 12. X is 20. Check this out. 0. The person's not moving. This line right here, not changing. The person isn't walking towards it or away from it. So the derivative of the y is 0 in this case. And then y squared is going to be 25 squared. Okay, I'm going to leave this one alone for just a second. Let's simplify the right. And we end up with 300 over 625. And we could probably simplify that to 12 over 25, I think. So let's talk about this for a minute. We need to figure out what that angle is. We also need to get it to the other side because the question, remember, is asking what is the derivative of the angle. So we have that over here. We would need to either divide by secant squared, so it ends up in the denominator here, and then you end up with a complex fraction now. Or you can look at it like this, and remember that secant is really 1 over cosine. So better would be to just multiply both sides by the cosine squared of this angle. So let's talk about how we're going to get this angle first. So the next thing I'll do is once I figure out what this angle is, I can multiply both sides by the cosine of that angle squared. And then it'll cancel over here. Okay, so remember that the tangent is x over y. Let's go back to this. Because we were given an x and a y. It was 20 and 25. So if we want to solve for theta, this is where you do the inverse Remember, inverse functions cancel each other. So like I've been saying a million times in previous videos, like the logs, the natural logs and the e's cancel. Well, the tangents and the inverse tangents cancel. So you just take the inverse tangent to both sides. Both sides. Happens fairly to everything. And then those cancel out, you're left with theta. And this is a nasty number. Just throw it in your calculator. At this point, make sure you're always in radian mode. Radians. Okay, so now we know that this is 0.6747-ish. We can multiply both sides by the cosine of that angle and then square it. Notice how I write it. The 2 is really on the outside. And at this point, you can just use your calculator. And now we know that the rate is increasing at about 0.3 per second, feet per second. So that means that this is getting bigger, obviously, because the firework is going up in the air. Okay, next one. Water is drained out of a tank shaped as an inverted right circular cone with a radius of 8 centimeters and a height of 12 centimeters at the rate of 6 centimeters cubed per minute. At what rate is the depth of the water changing at the instant when the water in the tank is 4 centimeters? Okay, lots of stuff. Here's our picture. So they gave us water is being drained out of a tank, a whole bunch of stuff, radius, a height, at the rate of, we were given the volume, the rate of the volume. Water is coming out of it. So that's a rate, it's a derivative, it's -6. We were told that the radius of this entire thing is 8, and the height of this entire thing is 12, the entire thing. But now think about it, there's water in here. There's water inside. So the radius is not always 8 of the water, because we're asked about at what rate is the depth of the water changing. The depth of the water is going to be the height. So we're actually asked to find this when at the instant when the water is 4. So they gave us what is the rate of the height of the water when the height is 4. So this will help us later, but this represents the actual tank, not the height of the water. So the height of the water is changing. The radius is getting smaller and the height is getting smaller because the water is coming out. So be careful. And notice there is no information about the rate at which the radius is changing. So this is always smaller. It's constant as the water drains, the radius and the height are both changing. Okay, let's organize a little better. I draw all over the place. The rate at which the water is being drained, the volume is changing at -6. It's getting smaller. The radius of the whole thing is 8. The height of the whole cone is 12. And they're asking us to find the rate of the height of the water at the instant when the height is 4, the height of the water. So we're talking about the height of the water, not the height of the cone, because the tank is not changing size. The tank itself is not changing, it's the water, the level of the water that's changing. Okay. The volume, we're going to need this because we have information about the volume and they're asking us for the derivative of the height. So we're going to need to plug this in to a volume equation. So the volume of a cone is 1/3 pi r squared h. And let's take this derivative. Before we take this derivative, think about what's going to happen. We have two variables here. Two variables, the 1/3 pi, that's a constant. So we'd have to do the product rule on the r squared and the h. When you do the product rule, remember it's going to be the first times the derivative of the second plus the second times the derivative of the first. Well, that's great. The first is r squared. We have an r. Kind of. We have an r of the cone. but not the water. Derivative of H is no problem. That's what we're looking for. That's an okay one to have. And then plus the second times the derivative of the first. Well, derivative of the first is going to be 2r and then dr dt. Again, we have an r, but this is of the tank, not of the water like we're being asked. We're asked to find the rate of the depth of water. So when h is 4, the radius is not 8. So we really can't use that here. And we also have no idea. Sorry about that. We also have no idea at the rate at which the radius is changing. We weren't given anything about the radius when the height was 4. So we have to do something to this equation. Before we take the derivative of this, we really shouldn't use the product rule because we're going to have unknowns. We can't use the 8 that we were given because it's of the whole tank and not the radius when the height is 4. And we have no idea how fast the radius is moving because in this case, the radius is definitely changing. So now this is where we use that 8 and 12 that they did give us. We're going to use similar triangles because if you think about it, this is a right triangle. When the height is 4, it's a similar triangle to when the height is 12. So you can set up a ratio, r over h, put the 8 and the 12 across, cross multiply, and we're trying to get rid of the r in this problem. So let's solve for the r. Take that and plug it in for the r. We're going to get rid of the r and make it an expression that's equivalent using similar triangles. So r, simplify that to 3/4. So now we plug that into the volume equation. The r is now 3/4 h squared. Remember this square here is the square here. Let's simplify this a little bit. That's 9 over 16, h times h. Simplify this one more time. This is now, cancel this and this. 3 pi over 16 and then h cubed. Now we can take the derivative, one variable, much better. Derivative of the volume. And now this is power rule, bring the 3 down. This is a constant, so it just stays for a minute. This is the 3h squared, and then we took the derivative of an h with respect to time. Plug in what we know. The derivative of the volume was -6. Here's my constant at the instant at which the rate or the height was 4. Simplify. This side is equal to 9 pi if you simplify a little bit here, because the 16 here and the 16 here cancel. And you can divide by the 9 pi and simplify here. I just swapped the sides. I don't know why I put the dh dt on the right, or I'm sorry, on the left. And I simplified 6 over 9 is 2 over 3. Final answer. The height of the water is decreasing because it's negative at a rate of 0.212 centimeters per minute when the water is 4 centimeters deep. Hopefully that makes some sense. That's your related rates section.